Okay, so let's kind of look at one more example in uh, in three space. Just notice here now we have a function of three variables x, y, and z, and the vector that's getting spit out has three components: an I, j, and a k component. Okay, so we want to RC here is the twisted cubic. So it's t squared, and t cubed. And so r prime of t is going to be 1, 2t, 3t squared. And if we want to kind of think of putting f in terms of t, the first component, the ith component, is going to be x times y, which is t times t squared. We're going to have t cubed. And then the jth component is going to be y times z, which is t squared times t cubed. That means t to the fifth. And then the last component, the kth component, is going to be x times z, which is t times t cubed. So those are going to be t to the fourth. Okay, and so our integral is going to kind of look like, remember, we have f dotted with r prime of t dt. And so if we go and switch our bounds, or switch our kind of integrating this with respect to t, when we take this dot product, well, I'm just going to write that first. And this was t cubed, t to the fifth, t to the fourth, started with 1, 2t, 3t squared. See? So I think we'll have t to the cube, t cubed, plus 2t to the sixth, plus 3t to the sixth. And so when we integrate, this is going to turn in t to the fourth over 4. And then this is going to be 5t to the sixth, which will integrate to 5t to the seventh over 7. Graduating from 0 to 1. So I think it's just going to be 1/4 plus 5/7. Which is going to be 27, 28. That's going to be, and that's going to be 20. No. 27 over 28. And so notice the last one was negative, which meant that that vector field was doing negative work, and this one is positive, which means it was doing positive work. Okay, so kind of this vector field was moving this particle. We can kind of think of it as going, helping this particle along, whereas when it's negative, that means it's kind of going against the particle. That means the particle is going in the opposite direction of the vector field. Okay, so let's kind of take a look at this, because this is going to kind of come full circle and connect back with something we looked at yesterday, or not yesterday, because none of us were here yesterday. On Friday. Were you? Yesterday, yeah, today was this month. Right, yeah. So we can kind of think of rewriting this as this vector, PQR. And again, these are kind of all functions of x of t, y of t, and z of t. So we can expand it out a little more. But let's just kind of take a look at this. And remember, this is going to be dotted with r prime of t dt. Okay, and so when we expand this out a little more, y, t, dt, t, comma, q of x of t, y of t, z of t, comma, r, x of t, y, and that's going to be dotted with, well, if we want to expand r of t out, r prime of t rather, because r of t is x of t, y of t, z of t. So r prime is just going to be the vector x prime of t, y prime of t, z prime of t. dt. Okay, so kind of take that into just a second. It looks pretty nasty. But when we evaluate this dot product, notice we're going to have p times x prime of t times x prime of t plus q times y prime of t, and then we get r of y of t times z prime of t. So that's just the dot product, and then all times dt. So that dt is still going to distribute everything here. Okay, still looks kind of nasty, but notice that when we distribute, and I'm going to simplify this really quick by just writing x, y, and z. We're going to have x prime of t times dt. Here we're going to have plus q of x, y, and z times y prime of t dt. D prime of t dt. But what is x prime of t dt equal to? We have a really simple way of writing that. That's just dx. And this right here is just dy. And this is just dz. And so what it kind of cooks down to is just the function t integrated against x plus the function q integrated against dy, and then plus the function r integrated against dt. That's integrating we have a vector field that's like PQR, and we have RP that we're integrating it over. Then it just kind of turns into this. It's a much neater and easier formula. And so we kind of looked at this already yesterday, or on Friday and on Thursday, kind of integrating these line integrals we have with respect to different variables. And so that's kind of integrating over a vector field. Just turns into integrating kind of the x component with respect to x, and the y component with respect to y, and the z component with respect to z. And so that's why remember I said how the intervals with respect to the different variables would come back and make a little more sense. Now what we can think about is, well, this vector field is doing this much work in the x direction. So if we want to kind of add its work, all we're going to be concerned about is integrating that in the x direction. And then, the j component is in the y direction, so it's doing q amount of work in the y direction. So we integrate q with respect to y, the same way with r and z. So it's kind of intuitive. So that's all there is with line integrals. And so I think that's where we'll stop for today. I have some practice problems for you all to work on, but I'm actually gonna go through and watch this video. Let's kind of watch this and let me know what you think. But are there any questions before we do that on this kind of stuff? It's pretty straightforward. And I think as we get through the rest of this chapter, even though it's going to get a little more technical, a little more abstract, it actually will kind of end up tying all these things together. The next few days are a couple of theorems that I think this will help tie everything together. So, okay, let me